Parsing and Generation Strategies in Computational Linguistics.
Applied Linguistics Group uploaded this video for BS English students. Dr. KHALID Malik, the founder, has a PhD in Applied Linguistics TESOL. Having more than 25 research papers, he taught at many foreign universities and is now in a postdoctoral study program abroad. Join Applied Linguistics Group at youtube.com/@1966 Pakistani or use a QR code to join our Facebook group at
Syntax and Parsing. The structural hierarchy. Language is structured at multiple levels, beginning in the case of spoken language with patterns in the acoustic signal that can be mapped to phones, the distinguishable successive sounds of which languages are built up. Groups of phones that are equivalent for a given language, not affecting the words recognized by a hearer, if interchanged, are the phonemes of the language. The phonemes in turn are the constituents of morphemes, minimal meaningful word segments, and these provide the constituents of words. In written language one speaks instead of characters, graphemes, syllables, and words. Words are grouped into phrases, such as noun phrases, verb phrases, adjective phrases, and prepositional phrases, which are the structural components of sentences, expressing complete thoughts. At still higher levels we have various types of discourse structure, though this is generally looser than lower-level structure. Techniques have been developed for language analysis at all of these structural levels, though space limitations will not permit a serious discussion of methods used below the word level. It should be noted, however, that the techniques developed for speech recognition in the 1980s and 1990s were very influential in turning NLP research towards the new corpus-based, statistical approach referred to above. One key idea was that of hidden Markov models, HUMPs, which model noisy sequences, example phone sequences, phoneme sequences, or word sequences, as if generated probabilistically by hidden, underlying states and their transitions. Individually or in groups, successive hidden states model the more abstract, higher-level constituents to be extracted from observed noisy sequences, such as phonemes from phones, words from phonemes, or parts of speech from words. The generation probabilities and the state transition probabilities are the parameters of such models, and importantly these can be learned from training data. Subsequently, the models can be efficiently applied to the analysis of new data, using fast dynamic programming algorithms such as the Viterbi algorithm. These quite successful techniques were subsequently generalized to higher-level structure, soon influencing all aspects on NLP. Syntax. Before considering how grammatical structure can be represented, analyzed and used, we should ask what basis we might have for considering a particular grammar correct, or a particular sentence grammatical, in the first place. Of course, these are primarily questions for linguistics proper, but the answers we give certainly have consequences for computational linguistics. Traditionally, formal grammars have been designed to capture linguists' intuitions about well-formedness as concisely as possible, in a way that also allows generalizations about a particular language, example, subject-auxiliary inversion in English questions, and across languages, example, a consistent ordering of nominal subject, verb, and nominal object for declarative, pragmatically neutral main clauses. Concerning linguist-specific well-formedness judgments, it is worth noting that these are largely in agreement not only with each other, but also with judgments of non-linguists, at least for clearly grammatical and clearly ungrammatical sentences. Pinker 2007. Also the discovery that conventional phrase structure supports elegant compositional theories of meaning lends credence to the traditional theoretical methodology. However, traditional formal grammars have generally not covered any one language comprehensively, and have drawn sharp boundaries between well-formedness and ill-formedness, when in fact people's, including linguists, grammaticality judgments for many sentences are uncertain or equivocal. Moreover, when we seek to process sentences in the wild, we would like to accommodate regional, genre-specific, and register-dependent variations in language, dialects, and erroneous and sloppy language, example, misspellings, unpunctuated run-on sentences, hesitations and repairs in speech, faulty constituent orderings produced by non-native speakers, and fossilized errors by native speakers, such as for you and I, possibly a product of schoolteachers inveighing against you and me in subject position. Consequently, linguists' idealized grammars need to be made variation tolerant in most practical applications. The way this need has typically been met is by admitting a far greater number of phrase structure rules than linguistic parsimony would sanction, say, 10,000 or more rules instead of a few hundred. These rules are not directly supplied by linguists, computational or otherwise, but rather can be read off corpora of written or spoken language that have been decorated by trained annotators, such as linguistics graduate students, with their basic phrasal tree structure. Unsupervised grammar acquisition, often starting with POS tag training corpora, is another avenue, see section 9, but results are apt to be less satisfactory. In conjunction with statistical training and parsing techniques, this loosening of grammar leads to a rather different conception of what comprises a grammatically flawed sentence. It is not necessarily one rejected by the grammar, but one whose analysis requires some rarely used rules. As mentioned in section 1.2, the representations of grammars used in computational linguistics have varied from procedural ones to ones developed in formal linguistics, and systematic, tractably parsable variants developed by computationally oriented linguists. Winograd's Sherdlu program, for example, contained code in his program MA language expressing. To parse a sentence, try parsing a noun phrase, NP, if this fails, return NIL, otherwise try parsing a verb phrase, VP, next, and if this fails, or succeeds with words remaining, return NIL, otherwise return success. Similarly, Wood's grammar for Luna was based on a certain kind of procedurally interpreted transition graph, an augmented transition network, or ATN, where the sentence subgraph might contain an edge labeled NP. Analyze an NP using the NP subgraph, followed by an edge labeled VP, analogously interpreted. In both cases, local feature values, example, the number and person of a NP and VP, are registered and checked for agreement as a condition for success. A closely related formalism is that of definite clause grammars, example, Pereira and Warren 1982, which employ prologue to assert facts, such as that if the input word sequence contains an NP reaching from index 11 to index 12 and a VP reaching from index 12 to index 13, then the input contains a sentence reaching from index 11 to index 13. Again, feature agreement constraints can be incorporated into such assertions as well. Given the goal of proving the presence of a sentence, the goal chaining mechanism of prologue then provides a procedural interpretation of these assertions. At present, the most commonly employed declarative representations of grammatical structure are context-free grammars, CFGs, as defined by Noam Chomsky, 1956-1957, because of their simplicity and efficient parsability. Chomsky had argued that only deep linguistic representations are context-free, while surface form is generated by transformations, for example, in English passivization and in question formation, that result in a non-context-free language. However, it was later shown that on the one hand, unrestricted Chomskyan transformational grammars allowed for computationally intractable and even undecidable languages, and on the other, that the phenomena regarded by Chomsky as calling for a transformational analysis could be handled within a context-free framework, by use of suitable features in the specification of syntactic categories. Notably, unbounded movement, such as the apparent movement of the final verb object to the front of the sentence in "Which car did Jack urge you to buy?" was shown to be analyzable in terms of a gap, or slash, feature of type NP, WH, that is carried by each of the two embedded VPs, providing a pathway for matching the category of the fronted object to the category of the vacated object position. Within non-transformational grammar frameworks, one therefore speaks of unbounded, or long-distance, dependencies instead of unbounded movement. At the same time, it should be noted that at least some natural languages have been shown to be mildly context-sensitive. Example, Dutch and Swiss German exhibit cross-serial dependencies where a series of nominals NP1, NP2, NP3 need to be matched, in the same order, with a subsequent series of verbs, V1, V2, V3. Grammatical frameworks that seem to allow for approximately the right degree of mild context sensitivity include head grammar, tree-adjoining grammar, tag, combinatory categorial grammar, CCG, and linear indexed grammar, LIG. Head grammars allow insertion of a complement between the head of a phrase, example, the initial verb of a VP, the final noun of a NP, or the VP of a sentence, and an already present complement. They were a historical predecessor of head-driven phrase structure grammar, HPSG, a type of unification grammar, see below, that has received much attention in computational linguistics. However, unrestricted HPSG can generate the recursively enumerable, in general only semi-decidable, languages. A typical, somewhat simplified, sample fragment of a context-free grammar is the following, where phrase types are annotated with feature value pairs. SVF V NP plus tongue poking smiley num n case subj VP VF V plus tongue poking smiley num n VP VF V plus tongue poking smiley num n V subcat underscore NP VF V plus tongue poking smiley num n NP case obj NP plus 3 num n DT plus 3 num n n num n NP num n plus 3 case C name num n plus 3 case C. Here V, N, P, C are variables that can assume values such as past, pres, base, past participle, i.e., various verb forms, 1, 2, 3, first, second, and third person, sing, plur, and subj, obj. The subcat feature indicates the complement requirements of the verb. The lexicon would supply entries such as V subcat underscore NP VF pres num sing plus 3 loves DT plus 3 num sing N plus 3 num sing mortal name plus 3 num sing gen fem case subj. The T's. Allowing, for example, a phrase structure analysis of the sentence, the T's loves a mortal, where we have omitted the feature names for simplicity, leaving only their values, and ignored the case feature. Figure 1, syntactic analysis of a sentence as a parse tree. As a variant of CFGs, dependency grammars, DGs, also enjoy wide popularity. The difference from CFGs is that hierarchical grouping is achieved by directly subordinating words to words, allowing for multiple dependence of a head word, rather than phrases to phrases. For example, in the sentence of Figure 1 we would treat the T's and mortal as dependents of loves, using dependency links labeled subj and obj respectively, and the determiner would in turn be a dependent of mortal, via a dependency link mod, for modifier. Projective dependency grammars are ones with no crossing dependencies, so that the descendants of a node form a continuous text segment, and these generate the same languages as CFGs. Significantly, mildly non-projective dependency grammars, allowing a head word to dominate two separated blocks, provide the same generative capacity as the previously mentioned mildly context-sensitive frameworks that are needed for some languages. Kuhlman 2013. As noted at the beginning of this section, traditional formal grammars prove too limited in coverage, and too rigid in their grammaticality criteria to provide a basis for robust coverage of natural languages as actually used, and this situation persisted until the advent of probabilistic grammars derived from sizable phrase-bracketed corpora, notably the Penn tree bank. The simplest example of this type of grammar is a probabilistic context-free grammar, or PCFG. In a PCFG, each phrase structure rule x, y1. Yk is assigned a probability, viewed as the probability that a constituent of type x will be expanded into a sequence of immediate Constituents of types Y1, YK. At the lowest level, the expansion probabilities specify how frequently a given part of speech, such as det, n, or v, will be realized as a particular word. Such a grammar provides not only a structural but also a distributional model of language, predicting the frequency of occurrence of various phrase sequences and, at the lowest level, word sequences. However, the simplest models of this type do not model the statistics of actual language corpora very accurately, because the expansion probabilities for a given phrase type, or part of speech, X ignore the surrounding phrasal context and the more detailed properties, such as head words, of the generated constituents. Yet context and detailed properties are very influential. For example, whether the final prepositional phrase in "she detected a star with binoculars, planets" or modifies detected or planets is very dependent on word choice. Such modeling inaccuracies lead to parsing inaccuracies, see next subsection, and therefore generative grammar models have been refined in various ways, for example, in so-called lexicalized models, allowing for specification of particular phrasal head words in rules, or, in tree substitution grammars, allowing expansion of non-terminals into subtrees of depth 2 or more. Nevertheless, it seems likely that fully accurate distributional modeling of language would need to take account of semantic content, discourse structure, and intentions in communication, not only of phrase structure. Possibly construction grammars, example, Goldberg 2003. Which emphasize the coupling between the entrenched patterns of language, including ordinary phrase structure, clichés, and idioms, and their meanings and discourse function, will provide a conceptual basis for building statistical models of language that are sufficiently accurate to enable more nearly human-like parsing accuracy. Parsing. Natural language analysis in the early days of AI tended to rely on template matching, for example, matching templates such as X has Y, or how many Y are there on X, to the input to be analyzed. This of course depended on having a very restricted discourse and task domain. By the late 1960s and early 70s, quite sophisticated recursive parsing techniques were being employed. For example, Wood's lunar system used a top-down recursive parsing strategy interpreting an ATN in the manner roughly indicated in section 2.2, though ATNs in principle allow other parsing styles. It also saved recognized constituents in a table, much like the class of parsers we are about to describe. Later parsers were influenced by the efficient and conceptually elegant CFG parsers described by J. Early, 1970, and, separately, by John Koch, Tadaro Kasami, and Daniel Younger, example Younger 1967. The latter algorithm, termed the CYK or CKY algorithm for the three separate authors, was particularly simple, using a bottom-up dynamic programming approach to first identify and tabulate the possible types, non-terminal labels, of sentence segments of length 1, i.e., words, then the possible types of sentence segments of length 2, and so on, always building on the previously discovered segment types to recognize longer phrases. This process runs in cubic time in the length of the sentence, and a parse tree can be constructed from the tabulated constituents in quadratic time. The CYK algorithm assumes a Chomsky normal form, CNF, grammar, allowing only productions of form NP-NQ-NR, or NPW, i.e., generation of two non-terminals or a word from any given non-terminal. This is only a superficial limitation, because arbitrary CF grammars are easily converted to CNF. The method most frequently employed nowadays in fully analyzing sentential structure is chart parsing. This is a conceptually simple and efficient dynamic programming method closely related to the algorithms just mentioned, i.e., it begins by assigning possible analyses to the smallest constituents and then inferring larger constituents based on these, until an instance of the top-level category, usually S, is found that spans the given text or text segment. There are many variants, depending on whether only complete constituents are posited or incomplete ones as well, to be progressively extended, and whether we proceed left to right through the word stream or in some other order, example, some seemingly best first order. A common variant is a left corner chart parser, in which partial constituents are posited whenever their left corner, i.e., leftmost constituent on the right-hand side of a rule is already in place. Newly completed constituents are placed on an agenda, and items are successively taken off the agenda and used if possible as left corners of new, higher-level constituents, and to extend partially completed constituents. At the same time, completed constituents, or rather, categories, are placed in a chart, which can be thought of as a triangular table of width n and height n, the number of words processed, where the cell at indices I, j, with j, I, contains the categories of all complete constituents so far verified reaching from position I to position j in the input. The chart is used both to avoid duplication of constituents already built, and ultimately to reconstruct one or more global structural analyses. If all possible chart entries are built, the final chart will allow reconstruction of all possible parses. Chart parsing methods carry over to PCFGs essentially without change, still running within a cubic time bound in terms of sentence length. An extra task is maintaining probabilities of completed chart entries, and perhaps bounds on probabilities of incomplete entries, for pruning purposes. Because of their greater expressiveness, tags and CCGs are harder to parse in the worst case, O, N6, than CFGs and projective DGs, O, N3. At least with current algorithms. See Vijay Shankar and Win 1994 for parsing algorithms for tag, CCG, and LIG based on bottom-up dynamic programming. However, it does not follow that tag parsing or CCG parsing is impractical for real grammars and real language, and in fact parsers exist for both that are competitive with more common CFG-based parsers. Finally, we mention connectionist models of parsing, which perform syntactic analysis using layered, artificial, neural nets, ANS, NNs, C. Palmer-Brown et al. 2002, Mayberry and Mikulánen 2008, and Bengio 2008 for surveys. There is typically a layer of input units, nodes, one or more layers of hidden units, and an output layer, where each layer has excitatory and inhibitory connections forward to the next layer, typically conveying evidence for higher-level constituents to that layer. There may also be connections within a hidden layer, implementing cooperation or competition among alternatives. A linguistic entity such as a phoneme, word, or phrase of a particular type may be represented within a layer either by a pattern of activation of units in that layer, a distributed representation, or by a single activated unit, a localist representation. One of the problems that connectionist models need to confront is that inputs are temporally sequenced, so that in order to combine constituent parts, the network must retain information about recently processed parts. Two possible approaches are the use of simple recurrent networks, SRNs, and, in localist networks, sustained activation. SRNs use one-to-one feedback connections from the hidden layer to special context units aligned with the previous layer, normally the input layer or perhaps a secondary hidden layer, in effect storing their current outputs in those context units. Thus at the next cycle, the hidden units can use their own previous outputs, along with the new inputs from the input layer, to determine their next outputs. In localist models it is common to assume that once a unit, standing for a particular concept, becomes active, it stays active for some length of time, so that multiple concepts corresponding to multiple parts of the same sentence, and their properties, can be simultaneously active. A problem that arises is how the properties of an entity that are active at a given point in time can be properly tied to that entity, and not to other activated entities. This is the variable binding problem, which has spawned a variety of approaches, see Brown and Son 1999. One solution is to assume that unit activation consists of pulses emitted at a globally fixed frequency, and pulse trains that are in phase with one another correspond to the same entity, example see Henderson 1994. Much current connectionist research borrows from symbolic processing perspectives, by assuming that parsing assigns linguistic phrase structures to sentences, and treating the choice of a structure as simultaneous satisfaction of symbolic linguistic constraints, or biases. Also, more radical forms of hybridization and modularization are being explored, such as interfacing a NN parser to a symbolic stack, or using a neural net to learn the probabilities needed in a statistical parser, or interconnecting the parser network with separate prediction networks and learning networks. For an overview of connectionist sentence processing and some hybrid methods, see Crocker 2010. Coping with syntactic ambiguity. If natural language were structurally unambiguous with respect to some comprehensive, effectively parsable grammar, our parsing technology would presumably have attained human-like accuracy some time ago, instead of leveling off at about 90% constituent recognition accuracy. In fact, however, language is ambiguous at all structural levels, at the level of speech sounds, recognize speech versus recognize speech, morphology, unwrapped versus unwrapped, word category, round as an adjective, noun, verb or adverb, compound word structure, wild goose chase, phrase category, nominal that clause versus relative clause in, the idea that he is entertaining, and modifier, or complement, attachment, he hit the man with the baguette. The parenthetical examples here have been chosen so that their ambiguity is readily noticeable, but ambiguities are far more abundant than is intuitively apparent, and the number of alternative analyses of a moderately long sentence can easily run into the thousands. Naturally, alternative structures lead to alternative meanings, as the above examples show, and so structural disambiguation is essential. The problem is exacerbated by ambiguities in the meanings and discourse function even of syntactically unambiguous words and phrases, as discussed below, section 4. But here we just mention some of the structural preference principles that have been employed to achieve at least partial structural disambiguation. First, some psycholinguistic principles that have been suggested are right association, RA, or late closure, LC, minimal attachment, MA, and lexical preference, LP. The following examples illustrate these principles. RA, he bought the book that I had selected for Mary. Note the preference for attaching for Mary to selected rather than bought. Ma, she carried the groceries for Mary. Note the preference for attaching for Mary to carried, rather than groceries, despite RA. The putative MA effect might actually be an LP-like verb modification preference. LP, she describes men who have worked on farms as cowboys. Note the preference for attaching as cowboys to describes, rather than worked. Another preference noted in the literature is for parallel structure in coordination, as illustrated by the following examples. They asked for tea and coffee with sugar. Note the preference for the grouping, tea and coffee, with sugar, despite RA. John decided to buy a novel, and Mary, a biography. The partially elided conjunct is understood as, Mary decided to buy a biography. John submitted short stories to the editor, and poems too. The partially elided conjunct is understood as, submitted poems to the editor too. Finally, the following example serves to illustrate the significance of frequency effects, though such effects are hard to disentangle from semantic biases for any single sentence. Improvements in parsing through the use of word and phrase frequencies provide more compelling evidence. What are the degrees of freedom that an object in space has? Note the preference for attaching the relative clause to degrees of freedom, rather than freedom, attributable to the tendency of degrees of freedom to occur as a multi-word.
Applied Linguistics Group uploaded this video for BS English students. Dr. KHALID Malik, the founder, has a PhD in Applied Linguistics TESOL. Having more than 25 research papers, he taught at many foreign universities and is now in a postdoctoral study program abroad. Join Applied Linguistics Group at youtube.com/@1966Pakistani or use a QR code to join our Facebook group at